All right, sorry about that. I don't know what went wrong. I was trying to speak, but I guess nobody could hear. Kidding. That is today is my shout out to all of our Encore students and those who just love musicals in general. Dear Evan Hansen, you will be found. Hashtag you will be found. One of my favorites. So if you haven't, you've got some downtime, check it out. So today, for seniors, will be our last official math lesson. After that, our second lesson of the week is going to be a little bit of a senior send-off. And then for everyone, I'm just going to kind of do a really simple assignment where you're just going to kind of answer 2 questions for me about what you've learned through this whole thing. And then after we do our senior send-off, juniors and sophomores will continue on for, I believe, 1 more week, which is kind of good because who knows what's going on. I'm kind of losing my mind. I can't even tell right now if this is the end of May or early June. Another Dear Evan Hansen reference. All right, so today we're going to take a look at the basics of sequences. So let's go. All right, so we said we're going to look at the basics of sequences. So first we'll define them. Then we'll see how we can find terms of a sequence, and then we'll classify some sequences. All right, so here we go. First off, if we were just to define a sequence, we could say that it is an ordered progression of numbers, or even more simply, you could just say it's a list of numbers. All right, it's a list of numbers. And so here we have 2 examples. Negative 2, 1, 4, 7, and then our next one, 2, 1, 2/3, 1/2, and 2/5. So what's different about those 2 sequences is that first one is considered a finite sequence because it has a set number of elements with a definite end, which means we can count the number of elements inside that list. So that first one has 4 elements inside its list, inside its sequence. That second one has those 3 dots at the end, which makes it an infinite sequence, which means it has no ending point. The pattern continues on forever. We cannot count the number of elements inside that list. All right, so our sequences, we're only going to deal with sequences that have some math behind them. If there was no math behind them that helped you get from term to term to term, then we really wouldn't be able to do anything with them, and there would be no reason for us to look at them inside pre-calculus. So all of the sequences that we will take a look at, the terms will be related to each other by some sort of operations or mathematical pattern that we can apply to get from one term to the next. All right, so we want to take a look at how we can maybe find terms of a sequence. Well, we can use rules or formulas to find terms of a sequence, and we can do that 2 ways. You can do a recursive formula, and a recursive rule or formula allows you to find a term provided you know the one just before it. Or you could do it with an explicit formula, which allows you to find a specified term. For example, if we wanted to find the 100th term without knowing the term before that. Depending on what term you're going to be asked to find, you're going to want to work with the easier type of formula. If you were asked to find the 100th term, you definitely wouldn't want to have to go about that recursively, because that would mean you would have to find all of the 99 terms before the 100th and able to find the 100th term. But with an explicit rule, it behaves similarly to function rules, except we won't be using the letters x and y anymore. But just like functions have input and output, you could put the term number of 100 into the explicit rule, and then the value of the 100th term would pop out. All right, so let's kind of see how these work. We're going to go with the sequence negative 2, 1, 4, 7, ... So it's an infinite sequence. And we're going to actually pretend that right now we only knew the first term and that we want to find the 4th term. And we're going to take a look at how we could do that from a recursive rule and an explicit rule for this sequence. All right, so we're going to first take a look at recursive. But recursive, we need to just kind of go down to the bottom first. Because recursive, it said we needed to know the term before to find the next term, the term after that. So we just kind of need to take a look at how we determine term numbers, comparing term numbers. So a sub n and a sub n plus 1. If we compare those term numbers, the subscripts, the n and the n plus 1, n plus 1 is bigger. All right, so when we compare n and n plus 1, since n plus 1 is bigger, the bigger term number, a sub n plus 1 is going to represent the next term, and a sub n, since n was smaller than n plus 1, is representing the previous term. So when we have our recursive rule for this sequence, we have a sub n plus 1 is equal to a sub n plus 3. So that's telling us the next term is equal to the previous term plus 3. So here we go. If we just started with our first term being negative 2, then if we wanted our second term, we would take the previous term, the first term, and add 3 to it. Our first term was negative 2, so negative 2 plus 3 gives us 1. Now we need to find our third term. Well, we can find our third term if we take the previous term and add 3 to it again. So our second term plus 3. Our second term was 1, 1 plus 3, 4. So now our fourth term, which is what we were overall trying to find, our fourth term we could get if we took the third term and added 3 to it. Our third term was 4, 4 plus 3, 7. Alright, so if we wanted to find the fourth term, we would need to make sure we knew the first, second, third, and fourth terms before we could find the fourth term. Alright, explicitly, again we said an explicit rule behaves more like functions. And functions have input and output. So your input is going to be your term number, and then your output is going to be the value of that term. So if we're trying to find the fourth term, 4 is going to be the input of our function. So we're going to put 4 in place of the n in our explicit rule. So then that's going to give us negative 2 plus 3 times the quantity 4 minus 1. We do that 4 minus 1 and we get 3. So we're now at negative 2 plus 3 times 3. Alright, 3 times 3 is 9, so negative 2 plus 9, we get 7. Alright, so we got 7, whether we did it with our explicit rule or with our recursive rule, and that was the fourth term inside the sequence as well. So let's practice finding some terms of a sequence. Here we're asked to find the first 6 terms and the 100th term of our sequence. Alright, again we're asked for the first 6 terms and the 100th term. Alright, if we are asked to find the 100th term, I'm really hoping that we don't have the recursive rule, that we instead hopefully have the explicit rule. Because if we were going to have to do this recursively, again that would mean we would need to know the 99th term. And if we needed the 99th term, we need the 98th and the 97th and so on. So we would have to have been able to have found those first 99 terms in order to find the 100th term if we were doing this recursively. So let's take a look at our rule here. Our rule, a sub n equals 4 over n plus 2. This does not have the previous term inside the rule. This is behaving like an explicit rule, which again behaves like a functions, where the input, the term number, is going to go into the rule, and then the value of that term is going to pop out. So we have an explicit rule here, which is awesome because again you need the 100th term. So to find the first term, we're just going to put 1 into the n, the term number. So a sub 1, the first term, 4 over 1 plus 2, we get 4/3. All right, our second term, we're going to now put 2 in place of the n. We can always reduce our fractions. All right, now we're going to put 3 in for the term number. And the fourth term, reduce. Our fifth term, our sixth term, put 6 in for the term number. Okay, so we can list them all individually. We also needed that 100th term. The 100th term, we put 100 in for our term number. 4 over 102, reduce. Okay, so we can list them. Here, how about and then we'll say 100th. All right, so here's our first, second, third, fourth, fifth, sixth, and our 100th term Since this was an explicit rule, all we were doing was taking the term number and putting it in place of the n. All right, so let's try again. Find the first 4 terms in the 8th term of the sequence. We're given the first term, it's -3, and then a sub n plus 1 is equal to a sub n plus 10. So when we take a look at this one, we have our first term, and then our rule has a sub n plus 1 is equal to a sub n plus 10. So they're showing us to get the next term, take the previous term and add 10. So this one is a recursive rule. All right, this one is a recursive rule. So let's see here, we need the first 4 terms. Again, we already have the first term, -3. So to get the second term, it's going to be the previous term plus 10. Our previous term was -3. All right, so we'll get 7. All right, so to get our third term, it's going to be the previous term plus 10. Our second term was 7, add 10. All right, then we need our fourth term. Our fourth term is going to come from the previous term plus 10. Previous term was 17. Okay, so we were asked for the first 4 terms and then the 8th term. Well, this is a recursive rule. We have a recursive rule. We can't find the 8th term right away. We can only find if we only have the recursive rule, unless we wanted to try to write the explicit rule from here. We're not going to do that just yet. We'll maybe worry about that in our next math lesson. So seniors, you don't have to worry about that. Juniors and sophomores will eventually get there. All right, so instead to find the 8th term from this recursive rule, we're going to need the 7th term. But in order to find the 7th term, we need the 6th term. In order to find the 6th term, we need the 5th term. In order to find the 5th term, we need the 4th term. We have the 4th term, so we just need to kind of continue this on. All right, so our 5th term is going to come from our 4th term plus 10. Our 6th term is going to come from our 5th term plus 10. Our 7th term is going to come from our 6th term plus 10. And our 8th term, finally, is going to come from our 7th term plus 10. All right, so we needed the first 4 terms. -3, 7, 17, 27, and then it was going to continue on. And then our 8th term, you can even show it as a sub 8. 8th term was 67. If some of you were kind of getting to the point where you were like, oh, I can come up with a shortcut, that shortcut would have been you being able to write the explicit rule, which again, we'll do a little later, just not in today's lesson. Okay, so we already classified sequences by the number of terms being a finite number of terms and an infinite number of terms, but we can also classify them by how they're made. So the 2 main types of how sequences would be made would be considered arithmetic or geometric. And an arithmetic sequence is going to be one in which the difference between the consecutive terms is constant. What does that mean? That means you are adding the same number each time to get to the next term. Or the sequence could be geometric. What does that mean? That means that the ratio between the consecutive terms is going to be constant. In simpler terms, what does that mean if that ratio between terms is constant? That means you're multiplying by the same number each time to get from one term to the next term. So let's take a look at some sequences. All right, let's determine if each of the following sequences is going to be considered arithmetic, geometric, or neither. Then if it is arithmetic, let's find the common difference. If it's geometric, let's find the common ratio. Okay, so again we need to determine if it's arithmetic, geometric, or neither. And if it is arithmetic, find the common difference, what we added each time to get from one term to the next. If it's geometric, find the common ratio, what you multiplied by each time to get to the next. All right, so let's take a look at our first one. Let's see here, what do we do to get from 3 to -6? That will also work to get from -6 to 12, 12 to -24, 24 to 48. Looks like we're multiplying there. Looks like we're multiplying by 2, but positive, negative, positive, negative, positive. So it looks like we are multiplying by negative 2. Right? 3 times negative 2, negative 6. Negative 6 times negative 2 is now positive 12. 12 times negative 2 is negative 24. Negative 24 times negative 2 is now positive 48. So this one is arithmetic. Whoops, we were multiplying. We're multiplying, that's not arithmetic. All right, multiplying, multiplying, geometric. All right, geometric and common ratio, negative 2. Right, let's change color. All right, let's see what's happening in our next one. Negative 11, how do we get from negative 11 to negative 4, to also get from negative 4 to 3, from 3 to 10, and from 10 to 7. If you can't easily tell from looking at the first 2 terms, you can jump farther along. You don't have to always work off the first and the second term. It might be easier here. All right, let's go from this term to this term, and then this term to this term. What do we do? It looks like to get from 3 to 10, it looks like we would add 7, and then 10 to 17, add 7 more. Right? So let's come back over here and try that. Negative 11 plus 7, that does get us negative 4. Negative 4 plus 7 does get us 3. So if we were adding something each time, that does make this arithmetic. Arithmetic, and our common difference is 7. All right, we were adding 7 each time. Okay, let's try it again. Change color. 54 to 18, 18 to 6, 6 to 2. I'm not 100% sure. I can't easily tell right here how to get from 54 to 18. 18 to 6 maybe, but I think it would be a lot easier to kind of figure out here. Let's see here. Maybe I could jump back. 18 to 6. We're getting smaller, so we're either subtracting or dividing. Subtracting would be subtracting 12. But 6 minus 12 is not 2. 18 to 6 would be dividing by 3. Okay, and then 6 divided by 3 is 2. Okay, 2 divided by 3, 2/3. All right, you could also say instead of dividing, since we said with geometric sequences that you are multiplying by the same thing each time, you could say that you are multiplying by the fraction of 1/3. And then if we multiply 2/3 times 1/3, 1 times 2 would still be 2. 3 times 3 would be 9. So that works there. And if we were to go back and double check, yes, 54 times 1/3 would give us 18. So this one is geometric. And our common ratio, all right, we're not going to say divide by 3, we're going to say that we multiply by 1/3. All right, how about this one here? 8 to 9 to 11 to 14 to 18 to 23. I don't know. I don't think, I don't know. I couldn't easily multiply 8 times with something to get to 9. I can't easily multiply 9 times something to get to 11. What's going on here? It looks like I'm adding 1. Then it looks like I'm adding 2. And then adding 3. And then adding 4. And then adding 5. Okay, so is there a pattern? All right, but are we adding the same thing each time? So is this going to be considered arithmetic? All right, not arithmetic because we are not adding the same thing each time. There is no common difference. All right, so this is not arithmetic. It's definitely not geometric because we weren't multiplying. We were adding. What were we doing? We were adding one more thing each time. All right, so this is neither. There's a pattern. All right, there's a pattern, but it does not fit the definition of arithmetic or geometric. Okay, last one. Let's see here how we're going to get from 4 to -1, then from -1 to -6, then from -6 to -11, -11 to -16. So we're getting smaller, so we're either subtracting or dividing. Dividing, same thing as multiplying by a fraction again. Well, let's see here. I'm going to go there. All right, what do we do to get from -1 to -6? It looks like we subtract 5. And then from -6 to -11, again, subtract 5. From -11 to -16, again, subtract 5. And here, from 4 to -1, we can subtract 5. So, common down below. And it is a common difference. You can talk about it as subtracting 5 or adding a negative. All right, so that still does fit our definition of arithmetic. And our common difference is -5. All right, so that is it for today. So again, seniors, this was your last official math lesson. We'll have a senior send-off that will still also apply to our juniors and our sophomores, and then it'll be a very easy assignment for lesson 2. And then juniors and sophomores will continue on into the week after that. But again, I love all of you. Hope you're doing well and staying safe. And I guess I'll sign off with one more Dear Evan Hansen reference. Again, love you all. Sincerely, me.